So now we're going to look into automation. Let's say what the safety and automation system is doing, and the automation, which is discrete control, starts up motors, controllers, control tank levels, or whatever it's doing. So again, it's going to be the compendium here. Safety, automation and supervision, and now we're going to look into automation. So automation, discrete and continuous control. Enable operators to control processes. Yeah, this is a brief introduction. What we're going to look at is basically discrete and continuous control. First, discrete control is start and stop of devices, equipment in the field. Here's a pump by an automation device of some sort, a PLC normally, by an operator. So it's pump control. Continuous control, there is an operator, automation device, here control a tank level by a control valve, and the operator doesn't have to do much. So there's a pump providing fluid into the tank. There is a ultrasonic sensor for the tank level or some kind of tank level measurement, and so on. This is all running automatic, and the operator, he can lean back and supervise the process. Okay, so that's tank level control. So automatic control is basically the same here. So what we looked at here, the automatic control, so there's an automatic tank control, tank control. So for automatic control, there is some requirement for instruments. We have control loops, we have fail to safe. We have something called pulse-operated actuators. We can use a pulse to start the equipment and not a pulse to stop it. And so on. This is, here's the pulse-operated outputs. So here we have a start. If the starts, it's interlocked by a close contact with let's say just when it starts, this one is just bypassed in parallel, and we have to open this one to stop. So which means that even if my automation device fails, this pump is going to continue to run if it's important that the pump runs. Of course, there would be a safety system also taking care of the situation if the situation worsens, then we have to do some safety actions here or something like that. Here, another principle here for, this is discrete control again, control signal and feedback. So we have some kind of hydraulic valve or flap or whatever we are doing, can be open and closed. So we give open and close commands, and we get open and close feedback that it is fully open and fully closed, because this is not a control flap or valve. This is a discrete one, fully open or closed. This is in a cabinet or something, let's say across wiring or something. You have a local remote switch if the automation device should control this. Controller devices, or device control, which should probably be called device control. We have a principle called object orientation. This is not a course in object orientation, but there's something in here. Object orientation means that we have a data, and we have got methods or small programs that you can use to operate on the methods. And then this is just a definition with data and methods, and then we can make instances of this. Here is, again, we use a motor or pump or something, so we can for a motor, we can have a pump motor, a fan motor, another pump motor, and then we have a class here that's called the motors. What they used to do in PLCs, and these are still doing, is to use global data memory and the function they're working on this memory, especially in ladder logic and FPD. Of course, you shouldn't program PLCs using FPD and ladder logic. There's a function that's destroying some data exchange area between two functions, and what problem this is going to cause, nobody knows, but it might even be hard to find, because you never know maybe it's just sporadious, spontaneous errors. It doesn't do it often, every leap year or something like that, and you're going to have a problem to locate it. Exchanging data is then through methods. You call a method to change the data, and the instance of the object just validates the data change. If you want to set a value to 100, but it can't be more than 50, you don't get more than 50, or you get a message, sorry, I can't set 50. So the method just works on the data. So this is called an information hiding. You can't access the information in the object directly. You have to ask the object, is it okay for me to change data or attributes or whatever you call it? Yeah. Automation object has a function block that you use, which is a collection of code in a function block. Some automation device suppliers, they can also implement methods here too. So there's code working on the data. So again, we have a class, a function block to make. We made an instance, an object, a valve. So when we looked at the valve here, we have open and closed and manual remote as input. We have a pressure that in our code maybe could open and close the valve, so we could do it from an operator station. This can be used over and over. Then also, when we construct classes, try to make general functionality. Let's say as an example, it's just an example. In the class has two feedbacks, open and closed, and then we run into a valve that has only one feedback, that's open. It's not too important to know if it's closed, but we need to know if it's open. And not open is not okay for us, so then we say it's closed. But remember, not open does not mean that it is closed. What we can do is to just invert the open feedback and use the same class. So we don't make a class or function block with only one feedback for valve. And there are other types too. For the control signals, of course, it has two control signals outputs. They could be pulsed, for instance, or steady. And if the valve here with only one feedback has only an open command, and not open command is close command, of course we use just one of the outputs to control this. But then it has to be steady on as long as the valve should be open, so it shouldn't be pulse operator. But of course, when we program a code, that's an option for us. Say, do we have steady outputs or just a single output? Or should they ask as a steady output or a single output? Yeah, as general as possible. Reuse them and test them. Control and feedback, we are at least here. When you do control, you should always confirm that your control effort has the desired effect. That's the principle. And what we have primary device feedback. Here, again, an example, we check that the device is actually in the position. Here's a damper. So we just checks that the damper here is open and we have airflow. And then also we could check the power supply or something to the damper to make sure that it has power to do what it's designed to do. And we have the feedbacks, fully open and fully closed. And that was the primary feedback. And then we have a secondary feedback. We don't have a feedback on the damper, but we have air pressure. So if the damper is open, we have air pressure, and we can use that as an input and say, okay, the damper is open. But remember, if there's no air pressure here, the damper can be open, but there's a problem with the fan. The fan, there's no air in here. So it's not as good as that. And in this case, maybe we should have two feedbacks for the damper and also air, because the damper can be open, but the fan is not running, so we don't have any air, which is our primary goal. But that it can be used as a secondary feedback. And then again, we talked about verification and control command. We have an open command and or out, and we get an open feedback, waiting for an open feedback for a delay. If you get it, it's nice. If you don't get it, it's an error reported to the operator. So when we have opened the valve, we have to monitor it for unsolicited or spontaneous errors. If we have said the valve should be open, but the valve closes, that's an error. Why it closes? The power disappears. It's been closed by someone other, who knows? it closed. I don't know why. But that's an error reported. So here it's delays. So we store the open information and say it should be open. We lose the feedback. It's a spontaneous close or unsolicited close. We report it. Then we have something here too for the discrete control that's called mode selection. Automatic, manual, and local mode. This is used usually by, let's say, manual, local, remote, and automatic. What it says in here, that it's just local and remote. It's not a switch. It's done via the HMI system. So the switch here is just remote, local. Remote controlled by the automation device, local, use a hand crank or operated by some other means. So what does it mean? I think, yeah, we can talk about it. What does automatic mode means? Automatic, or we can start with local. We looked at the local mode, but in remote mode. Manual mode, a device is, or the valve here, for instance, is operated from by an operator on an operating system. Remote controlled. Okay, automatic is blocked. So if we select automatic mode, the operator can't open and close the valve, but the pressure switch can do so. So this is the code. And again, object and data. So the object is programmed to have manual, automatic, and also local mode, transparent mode, outside mode. You can call it whatever you want. Transparent, it's just observe the feedbacks and something like, can't do any control in remote. But you should observe the feedback, see if it's open or closed by someone else. So that was control in general, and basically had discrete control that we looked at. So yes, we looked at discrete control, where we also had a little about continuous control with controllers, but that's for a new video, automatic control. So automatic control here is not a controller that we control a tank level mainly, but it's automatic control of, let's say, discrete devices. So a discrete device, a motor, could start and stop automatically, but often there are controllers involved in the system.